In section 2.4, we're going to look at what does the derivative mean in application problems and introduce a new kind of notation. So in this section, we're going to use the difference quotient to interpret the meaning of a derivative in an application problem. We're going to investigate what the units should be in those problems and what they represent in a real-world scenario. And we're going to interpret what the sign of the derivative is going to mean. And we're going to do all of this learning a new kind of notation called the Leibniz notation. So first, let's recall the derivative definition. F prime of x is equal to the limit as h approaches 0, f of x plus h minus f of x over h. We could say this in a different way, as this is the limit as h approaches 0 of the change in the y values over the change in the x values. Let's remember that h really is the difference between the x values that we're talking about. So, said in a different way, this is the limit of delta y over delta x. That is the derivative there. And if we think about a quick graph, what's going on? We have some function, and we are looking at a point x and its counterpart x plus h. And we are using the corresponding function values and the secant line between those. And if that secant line is closer and closer together, the 2 points are closer and closer together, this becomes the tangent line. So what we have here is a little triangle that's going to be very useful to think about, a right triangle, where the bottom of that triangle is delta x. It's the change in the x value. It's, in this case, x plus h minus x, or just h. And the other side is going to be the delta y, the change in the y values. In this case, that's going to be the f of x plus h minus f of x. So what we're doing is we're finding the slope. That's the derivative. And the slope is going to be rise over run, or the change in y over the change in x. And note that if we let that distance between x and x plus h go to 0, then we actually get the derivative itself. And that's why we need the limit as well. So we have delta y and delta x represent a very small change in y and x respectively. However, if we let this change get infinitely small, so now it's just not a small change, like maybe a small change might be 0.01 or something. What if we let it be infinitely small? In that case, we have something called an infinitesimal. And these are going to be dy and dx. So said differently, if I have a small change in x, delta x, and I let that small change get infinitely small, then what I am left with is dx, and dx represents an infinitely small change in x. And this is all to get us used to this idea of Leibniz notation. So calculus came about thanks to two people mainly, that is Gottfried Leibniz and Isaac Newton. And Leibniz pioneered this notation, this dy dx notation, and it is very useful in calculus. I think at the beginning, a lot of students like to just tend toward the prime notation. It's easier to write, it's easier to understand, but the dy dx notation is more useful in a lot of different circumstances, which we'll investigate later in the course. So here, the derivative, f prime of x, we are going to look at is dy dx. And note that that's a very similar idea to the limit of delta y over delta x. As we said on the previous page, if I let delta y get infinitely small, I get dy, and if I let delta x get infinitely small, I get dx. So dy and dx have the limit kind of built in to that notation. Also note that if I have the derivative of f of x at x equals a, that's f prime of a, we can write that as dy dx with a vertical bar x equals a. This is called an evaluation bar. It means to plug in x equals a. And to be completely upfront, this notation we are not going to use nearly as often, as it's kind of gross to have to write that vertical bar, but it will pop up here and there. So let's look at something else of this Leibniz notation that's very, very useful, which we're going to look at a lot, especially in chapter 3. dy dx, remember, is the derivative of the function f prime. And what's really nice about the Leibniz notation is that you can do some algebra with it. You can break it up in different ways to make this very nice. And one thing you can do is you can bring the y out in front. So write it as ddx of y. And note that in these problems, we have y is a function of x. Y equals f of x. So we could replace y with f of x. And then this is another way of saying the derivative of f of x with respect to x. In general, if you have ddx of something, this means the derivative of, and the x here tells you what variable you're talking about. This is called an operator, ddx. You slap it onto something, and it tells you to take the derivative of that something. So now let's look at units with derivatives, and we'll look at an application problem. So we have the cost of extracting T tons of a mineral is C, we're going to do, capital C here, is F of T dollars. So real quick, what we have is T is the independent variable representing tons. This is like our X here. And C is the dependent variable given in money, dollars. This is going to be like our Y. So first, let's interpret just what this function value means. If I have f of 100 equals 2,000, we have that f of 100, this is a t value, and we output a c value. So this is the cost of extracting 100 tons of a mineral is $2,000. Now let's look at the new thing, which is how do we interpret the derivative? So let's say we had f prime of 2,000 equals 100. And we're going to use this Leibniz notation to kind of help us out with understanding what this means. So first, let's rewrite it in the Leibniz notation. This is f prime of 2,000 is dc dt. That's like dy dx. Remember, c is like y, t is like x. Evaluated at t equals 2,000. And if we do that, we're going to get $100 per ton. Dollars per ton, and we can think about that as dc dt. The units are going to be dollars over tons. So that's going to be our units for the derivative. So another way of kind of saying this is at t equals 2,000, when we extract 2,000 tons of material, if we have a small change by delta t units, then we are going to have that delta c over delta t is going to be about 100. So let's say that again with a little graph maybe. We have our function f of t. We have 2,000 here. We're saying at 2,000, if we go up delta t units, if I go over delta t units, I'm going to go up delta c units. Right, so that's what it's saying. At t equals 2,000, when you go to the right delta t units, you go up delta c units. And in this case, delta c over delta t is going to be about 100. That's the value of the derivative. That's how much we are changing there. That's the slope of that line. Now, if we multiply delta t on both sides, we have delta c is going to be about 100 delta t. So what does this mean? This says that when we have 2,000 tons of minerals, that's just saying that we are at t equals 2,000. So that's just the fact that we are at 2,000, or at 2,000, we have 2,000 tons of mineral have already been extracted. So when that is the case, the additional cost, that is delta C, of extracting the ton is approximately $100. So if I need to add one more ton to be extracted, the cost of that is $100. Think about that in the graph. We have some function, f of t. Here's 2,000. If we extract one more, that means that we are going to go up 100 units in C. And that's because the slope here is 100 over 1, or 100. So the derivative, one more time, is at this point, when 2,000 tons have already been extracted, because it changes if it were something different, the additional cost of extracting one more ton is approximately $100. We'll look at some more practice problems with this kind of thinking in the next video.